This is Econ 510 Managerial Economics class. Today is February 24th, Thursday. The class will review for the second midterm exam, which is scheduled next Tuesday. So exam 2 covers chapters 4, 5, and 6. Here are summary of those chapter video.
Utility theory is the tool economists use to describe the way households allocate their limited budget across the array of goods and services that provide satisfaction. Why is it that most consumption bundles are balanced? They contain some apples, some oranges, some milk, some eggs. Why don't consumers spend all of their income on one particular good or service that's especially satisfying and buy very little of anything else? Utility theory can help explain the balance in people's consumption bundles. Utility theory has at its root a unit of measure called the util, and a util is an increment of satisfaction. For instance, if I have a potato chip, and I do like them, I might measure my satisfaction by creating this fictional measure of happiness called the util, and the first potato chip that I eat adds 10 utils to my satisfaction. Think of this as a kind of psychic payoff from the pleasure of eating a chip. The marginal utility of consuming a potato chip is the additional utility, the extra number of utils that are added to my total satisfaction when I consume that first potato chip. So its marginal utility, or psychic satisfaction, is equal to 10. That means if I eat one potato chip, my total utility is 10 utils. So good. Now, suppose I decide to have a second potato chip. I'm sorry, so good, but not quite as good as the first one. I mean, after all, marginal utility does diminish. The second potato chip is never quite as good as the first one, even though it's still quite delightful. The total utility that I get from eating 2 potato chips is 10 for the first plus 8 for the second, for a total utility of 18. Of course, no one can eat just 2, right? The third chip adds only 6 utils to my total satisfaction, bringing the complete level up to 24. I mean, it's better than nothing, but not quite as good as the first 3. My total utility, however, is still increasing for a while. I mean, it was there, right? So I ate it, but I can't say it was especially enjoyable. Okay. Can I have a glass of water? I mean, is the point clear? More is better, up to a point. But each additional unit provides a little less satisfaction than the unit before after some point. Consumption is subject to diminishing marginal utility. Each additional unit that you consume in a set period of time, other things held constant, is going to provide less satisfaction than the unit before. This means that While more of everything may be better, eating more potato chips at any given point of time, after some point, becomes a bit of a chore. Marginal utility can fall to zero and even become negative. So now we'll show how to apply this tool as we calculate the way consumers choose to spread their income out over its competing uses. But first, I'm going to take a break. We're ready to tackle the problem of consumer choice. That is, how will a household allocate its scarce income across the goods and services that provide it with satisfaction? For instance, how much of our snack budget will we spend on apples and how much will we spend on candy bars? The answer to this problem hinges on utility theory, and it turns out that the rule the household uses to allocate its income across competing uses is this one. The household will continue to shift its money between spending on apples and spending on candy bars until the marginal utility per extra dollar spent is equal across the two goods. Let me give a simple example to show how this principle works. Suppose we're going shopping and we have a limited budget, say $6, to spend on apples and candy. How much will we spend on each? How many candy bars will we buy and how many apples? Suppose we start putting candy bars into our shopping basket. It costs $1 to buy a candy bar, and the first candy bar that we put into our shopping basket gives us a psychic satisfaction of 10 utils. So right now we're getting 10 utils per dollar from our purchase of chocolate. Suppose we also put an apple into our shopping basket, and the first apple that goes in provides us with psychic satisfaction of 8 utils. Now, since apples only cost 50 cents, these 8 utils average out to 16 utils per dollar. That is, at the moment, we're getting more marginal utility per dollar spent on apples than we are on chocolate. So let's go ahead and put another apple into our shopping basket since they're such a good deal at providing us with satisfaction. The second apple also costs 50 cents, and it provides us with a little bit less psychic satisfaction than before, only 6 utils. Well, 6 utils for 50 cents comes out to 12 utils per dollar, which is still more than we're getting from chocolate. So we'll go ahead and buy another apple. This third apple provides us with an extra utility of only 3 utils. So 3 utils for 50 cents amounts to 6 utils per dollar. Now chocolate looks like a better deal. So let's go ahead and buy another candy bar. For $1 spent, this next candy bar provides us with psychic satisfaction of 8 utils. 8 utils per dollar is better than 6 utils per dollar, so chocolate still looks like the best buy. Keep spending on chocolate. Here we spend another $1, and the third chocolate bar provides us with a marginal utility of 5. So now we're getting 5 utils per dollar from chocolate, 6 utils per dollar from apples. That means apples are looking good again. Let's put another apple into our basket. And this apple is going to give us a psychic satisfaction of 1 util. 1 util for 50 cents spent is 2 utils per dollar. So now chocolate is now the preferred way of spending our snack money once again. Spend another $1 on a candy bar, and that gives us a psychic satisfaction of 2 utils. 2 utils per dollar on chocolate is equal to 1 over 50 cents, or 2 utils per dollar on apples. So now at the margin, an extra $1 spent on either snack is providing us with the same amount of satisfaction. Over here we'd get 2 utils from spending $1 on apples, and over here we'd get 2 utils from spending $1 on chocolate. Good thing that we've equilibrated the two, because now we're out of money. That is, the consumer is going to keep shifting money between the two until marginal utility divided by price is equal for the two goods. There's no reason for us to do without an apple so we can have more chocolate, because then apples would be providing more satisfaction than chocolate at the margin. We'd want to go right back to what we were doing before. And there's no reason for us to do without a candy bar to have an extra apple, because the candy bar we'd be giving up is providing us with more satisfaction per dollar spent than an extra apple would. And if we add up the money spent, 50 cents, 50 cents, 50 cents, and 50 cents, plus $1, $1, $1, $1, we've now spent our entire snack budget of $6, and we've allocated it across apples and across chocolate in such a way that the marginal utility for an extra apple divided by the price is equal to the marginal utility of an extra chocolate bar divided by the price. We spent our limited income, and we spent it across two goods in such a way that an extra dollar spent provides us with the same extra satisfaction, whether we're buying apples or chocolate. This is the rule that households use to maximize satisfaction from a limited amount of income. We're back with our indifference curves and our budget constraint, and we're getting ready to derive the consumer's demand curve. Remember what we did last time. We showed that if you have a set of opportunities created by your income and prices, and a set of preferences, you're going to look for the most satisfaction you can get, given your constraint. That point of maximum satisfaction will be where your budget constraint touches the highest attainable indifference curve. Now, what's going to happen if your opportunities change? How will your behavior change if the constraint changes? In particular, how will Chris behave if we reduce the price of toys? Let's cut the price of toys in half, from $3 a piece to $1.50 each. What would Chris do in those circumstances? First, let's show in our graph the new budget constraint. With a price of $1.50 each for toys, the vertical intercept remains unchanged. We haven't done anything to the price of snacks or to Chris's income, so if he spends all of his income on snacks, he can still afford 12 snacks. However, if he spends all of his income on toys now, at a price of $1.50 per toy, he can afford to buy 8 toys instead of 4 like before. So here is Chris's new budget constraint. Our blue line here represents his opportunities with an income of $12 and a price of toys of $1.50 each. What's Chris going to do? As usual, he's going to look for the combination of toys and snacks that gives him the most satisfaction subject to this budget constraint. And that means looking for the highest attainable indifference curve. Well, it's clear that the highest attainable indifference curve in this picture is the one that's labeled U1. And the combination right here, 2, 4, 6 snacks and 2, 4 toys, that is 4 toys and 6 snacks, this particular combination represents Chris's optimal choice. Let's make sure that point's attainable. Of course, it's on the budget constraint, so we know that it is. 4 toys times $1.50 each gives us a total of $8, and 4 snacks at $1 apiece gives us a total of $4. 4 plus 8 is 12. Once again, Chris satisfies his budget constraint. How do I know that this particular combination is the best Chris can do? Because it represents a point of tangency between an indifference curve and the budget constraint. This is the point at which Chris's marginal rate of substitution, that is his willingness to trade toys for snacks, is equal to the relative price of toys and snacks. That is what the market will permit. You always find the optimal point where the indifference curve is tangent to the budget constraint. That's always the best that he can do. So, even though there are other indifference curves that are way up here to the northeast, Chris can't reach them because he doesn't have enough money. Even though there are other indifference curves that are below, they're irrelevant because they intersect the budget constraint. They're lower. Chris can get to a high level of satisfaction, the highest he can attain, by finding the point where the indifference curve touches the budget constraint at only one point. U1 is the highest level of satisfaction he can get. Notice what I did here. I changed the price of toys, and I looked at how Chris's optimal choice changed. He buys more toys than before. Before he was only buying 2. Now that the price of toys has fallen, Chris buys 4 toys. What I'm getting to is a demand curve. When the price changes, the quantity demanded responds, and that's what a demand curve is. In the next lecture, we will put the indifference curve budget constraint diagram that we have here before us, we'll put it on top of another axis and use this apparatus to derive a demand curve. What we're going to be seeing is the foundation for the demand curve, that is, where it comes from using this more basic theory. Suppose you have a business and you're producing something, maybe hamburgers, maybe television sets, and you'd like to know, how much should I produce so as to make the most profit I can from my operation? We're now entering a set of lectures that's going to equip you with the tools economists use for describing the behavior of profit-maximizing firms. In order to get to the question of what a profit-maximizing firm should do, we have to back up and start with some basics. The first thing we'll do is describe the technology of the firm. That is, what can the firm do with a given set of inputs to produce a certain amount of output? We're going to describe the technical or technological possibilities that a firm has for producing output from input. That is, for assembling television sets or making hamburgers. Once we have a description of the firm's technology, we will then look at the cost to the firm of producing output. What we do is we take the technology and combine that with knowledge of the prices that the firm has to pay for its inputs, like labor, raw materials, capital, and come up with the cost per unit of making hamburgers or televisions. Finally, we'll combine the information we have about the costs of production with information about the price at which the firm can sell its product. Once we've combined those pieces of information, we'll be able to predict the best course of action for a profit-maximizing firm. We'll be able to answer the question, how much output should a firm produce if it wants to maximize its profits, subject to its technology, the price it pays for its inputs, and the environment, the competitive environment in which it finds itself. So let's back off then of this big picture and focus on the first set of specific questions we'd like to ask. That is, what are the technological possibilities of a firm? That is, what can the firm do? We're looking now at a firm's technology, and a technology simply means a catalog of things that a firm knows how to do. What we're most interested in is how much output a firm can produce with a given amount of input. Now, this sounds a lot like engineering, doesn't it? It's because it is. Economics, when we describe production, begins with a purely engineering relationship. That is, a relationship that has nothing to do with economics and money and stuff like that, but has more to do with technological possibilities. What can the firm do, according to the laws of physics, according to its know-how, to turn labor and raw materials into its finished product? Now, we're going to start with a careful description of a firm's technological possibilities. And then we're going to look at how to represent those technological possibilities in a graph. Finally, we'll introduce some concepts that economists focus on when they describe the technology that a firm uses to produce its output. Let's start then with a chart that shows the technological possibilities that the firm faces. It's kind of like a production possibilities chart for the firm. And we call this production possibilities a total output relationship. Total output is defined as the total amount of output that a firm can produce using a given amount of input, subject to its technological know-how, and any other factors that constrain its production. What a firm can do, given its know-how, with a certain amount of input. Total output, therefore, is the amount of output a firm can produce with a given amount of input. Let's look at the technological possibilities of a particular firm. Let's say this firm produces television sets. So their output in this case is TVs. And their input, let's say, is labor. Now, when we describe this relationship, total output, we're talking about what labor can produce, what a given amount of labor can produce in terms of television sets. But clearly, we need other inputs to make a television. We need raw materials, we need tools, we need a place to work. Whenever we describe the total output relationship in economics, we are usually talking about the short run. The short run is a period of time that is so short that you can only vary one or a few of your inputs. A plant that's producing televisions might decide over time that it wants to expand its operations, add another conveyor belt, get some more tools, build another warehouse. Well, you can do all that stuff in time, but in the short run, if you got a big order for television sets, you could only meet that big order by hiring more workers to come in and work with the factory as it exists now. The short run is a period of time during which some inputs are fixed and other inputs are variable. So when we describe the total output relationship, the first thing we want to do is to distinguish between fixed inputs and variable inputs. Let's suppose now that we are in the short run in our television production process. We're building TVs and suddenly we get an order to increase the number of televisions we're making. Maybe we get a big order from a department store. In the short run, let's suppose our only option for increasing output is to add more labor. Everything else is fixed in the short run. It's too expensive to alter quickly the number of conveyor belts, the size of the factory, the number of tools, and so on. So, for all practical purposes, our only variable when we're altering our output is labor, and we will call labor the variable input. Now, let me go back and define total output one more time. The total output of the variable input labor is the total amount of output that a given amount of labor can produce, holding constant technology, that is the firm's know-how, and holding constant the quantity of all of the other inputs that the firm uses, capital, the size of the factory, tools, anything else. We're going to consider those the fixed inputs. And whenever you write out a schedule like the one in front of me here, you're assuming that those fixed inputs remain fixed in the short run. So we've got a certain factory size, a certain number of conveyor belts, a certain pile of raw materials to work with. But in the short run, we can only produce more televisions by adding more labor. Let's look then at what the possibilities are in the short run. In the short run, if you have one worker, you can make 2 television sets per week. If you add a second worker with the same tools and the same technological know-how, you can make 10 television sets in a week. Employ a third worker, and the 3 of them can produce a total of 30 television sets in a week. 4 workers have a total product of 40 televisions per week. 5 workers will give you a total output of 45, and with 6 workers, you can make 48 television sets per week. As you see, as the numbers get larger, up to a point, the total output of labor increases. Oddly enough, if you go past a certain point, with 8 workers in this story, the total number of television sets actually drops by 1 from 49 to 48. This table of numbers, then, is a total output schedule. It shows you the total amount of output you can produce with given amounts of the variable input labor, holding constant technological know-how, and holding constant the amount of all other inputs used. The next thing I'd like to do is represent this information graphically. So, in the next lecture, we'll take this chart of numbers and put it into a picture. That picture will represent the production possibilities of the firm in the short run, and we will call that the total product curve. We're here in the factory because we're talking about production possibilities. Remember, we're talking about what a single firm can do in the short run when it's constrained by having some of its inputs fixed. The factory space is fixed. The number of conveyor belts is fixed. The tools are fixed. Maybe even our inventory of raw materials is fixed. But in the short run, we can vary our output by varying the amount of labor that we hire. Let's look now at the firm's production possibilities in the short run. Last time, we looked at this chart, which showed what a given number of workers could produce in a week, holding constant technology and the fixed inputs. Now we're going to take the information that's in this chart and transform it into a graphical snapshot of the firm's production possibilities. And we will call the picture that we draw the total product curve. Let's start now by labeling the axes. Remember, you always label your axes first, or you're not drawing an economic graph. You may be making art, but nobody knows what it is. Let's start by labeling the vertical axes. The vertical axis will measure the total amount of output that the firm produces. The horizontal axis in this picture will measure the total amount of labor that we are using to produce television sets. So here we have 1, 2, 3, 4, 5, 6, 7, 8 workers, and on the vertical axis we'll have 10, 20, 30, 40, 50 television sets. Let's now take the information from the total output chart and translate it into a curve. So the first point on our curve will be 1 worker and 2 television sets, and I'll put a red dot right here at this point to represent this possibility. If the firm employs 1 worker in a factory of a given size with a given quantity of tools and so forth, they will get 2 televisions per week. If you add a second worker, your total output per week is going to go up to 10 televisions, according to the chart. The third worker increases total output to 30 televisions per week. The fourth worker adds a total of 10 more televisions to give us a total output of 40 televisions per week. Notice now we're getting combinations of quantity of workers and quantity of televisions produced per week. The fifth worker makes it possible for us to produce a total of 45 televisions per week. With a sixth worker, we can produce a total of 48 televisions per week. 7 workers means we get 49 televisions per week, and 8 workers puts us back down to 48 televisions per week. These, of course, are not the only possible quantities of labor that we could hire. We could hire fractional workers. We could hire fractional workers by hiring people for only part of the day, or to only work part of a shift. If we connect these dots, we'll get a smooth relationship between the amount of labor that the firm employs and the number of televisions that are produced per week. So let's connect the dots then and get a total product curve. And here it goes, connecting the dots. And I'm going to label this curve TP because it is the total product of labor in my television factory. Every time I add a worker, I calculate the total number of televisions that my entire crew can assemble per week, and that gives me a point on the curve. So 1, 2, 3, 4, 5 workers can produce a total of 45 televisions per week. Now, when you look at this snapshot, you'll notice a few things about the production technology, the production possibilities. What do you see looking at this snapshot? What do you see that catches your attention? Well, let's notice 3 things. The curve has an S shape, and this kind of S shape is made up of 3 characteristics. The first thing you notice is that whenever you have small crews, adding an extra worker that is going from 0 to 1 and then 1 to 2 workers, output increases at an increasing rate. That is, each additional worker adds more to total output than did the worker before. The curve is increasing That is, the slope of the curve is increasing, the quantity of televisions produced are increasing at an increasing rate. So in this region down here, the curve is convex. Convex, the curve is convex. The slope is increasing. The next thing you notice is that over a range up to here, the total number of televisions produced is increasing at a decreasing rate as we add extra workers. That is, each additional worker adds less to total output than did the worker before. We're adding more workers, but the extra televisions that we're getting are fewer and fewer and fewer. Output is increasing at a decreasing rate. Finally, you notice that this curve has a maximum point, that there is some kind of capacity to our factory. If we hire too many workers, that is beyond a certain point, the total quantity of televisions produced actually begins to shrink. That is, if we go from 7 workers to 8 workers, the volume of televisions that we ship out the door actually begins to contract. Now, this requires some explanation. Economists usually draw the total product curve for a particular firm as having this S shape because it represents assumptions about technology that we believe match pretty well the reality of a lot of production processes, certainly production processes that involve manufacturing or making things. Let's then define a concept that will be useful to us in describing the shape of this curve, and that is the concept of the marginal product of labor. The marginal product of the variable input, in this case, the marginal product of labor, is the change in total output that results from increasing the amount of variable input by 1 unit. It is the change in total product that results from a change in the amount of the variable input, the amount of labor that's used. Let's calculate now the marginal product along this curve. The first worker takes our total television production from 0 to 2. The marginal product of the first worker then is 2 television sets. That's the total amount of output that he adds by being hired. The second worker, now that we have a shift that has 2 workers instead of 1, brings the total up to 10 televisions produced. That is, the second worker is adding 10 minus 2, or 8 televisions to total production. The marginal product of the second worker hired is 8 televisions. The third worker now brings the total up to 30. 30 minus 10 is a total additional production, or an additional production of 20 units. That third worker has a marginal product of 20 televisions. If it were for the third worker, we'd be back with 2 workers and 10 televisions. So the third worker adds 20. The fourth worker then adds 40 minus 30, or 10. The marginal product of the fifth worker is 45 minus 40 televisions, or 5. So the change in output that results from the change in labor is what we call the marginal product of labor. Remember, we're calculating this marginal product, holding constant the firm's know-how and holding constant all other inputs, like the size of the factory, the number of tools, and so forth. Here's a little chart that we've made up that shows the marginal product of labor. I could have labeled it marginal product, but I decided instead to label it with the definition of marginal product, the change in total output, or televisions, that results from a change in the labor input. If we do this, I can go over and lay this chart next to my other charts, and we see that the first worker has a marginal product of 2 televisions. He adds 2 to total output. The second worker has a marginal product of 8, as we calculated before, and you can go right on down the chart. The third worker has a marginal product of 20, the fourth has a marginal product of 10, the fifth has a marginal product of 5, and you can look at the rest of the chart, which we'll now move over next door so that you can study it. Here's what you want to notice about this firm's technology. We can describe a firm's technology by changes in its marginal product. Back there, whenever we were looking at the shape of the curve, we were really talking about changes in the firm's marginal product of labor. Let's look at that curve again. Down here, in this region of the curve, where the curve is convex, the marginal product of labor is increasing as we add additional workers. That is, down here in this region, each additional worker adds more additional output than the worker before. The first worker has a marginal product of 2, and then 8, and then the third worker adds 20, and so forth. Now, why does the economist believe that at small scales down here, whenever the firm is first adding variable input, that the marginal product would be increasing? Why is that? Do you have an idea? This is why. Economists believe that increasing marginal product comes from specialization and teamwork. Whenever you add additional workers to a production process, the workers are able to divide the task or divide the production process into lots of separate tasks, which they can do separately. For example, the famous example that Adam Smith gave was the production of straight pins, pins used for pinning clothes. He said the production process involves a lot of distinct tasks: stretching the wires, putting a point on the pin with a grinder, putting a head on the pin with a different tool. And he said, if you notice, the process of producing pins can be divided up into a lot of different tasks. And when each worker can concentrate on a particular task, perhaps a task that he or she is particularly good at even, has comparative advantage in that case, he says, the productivity increases remarkably. 3 workers can make 50 times as many pins as a single worker working alone. That's because they can divide the job into different tasks and save on the time they would otherwise spend doing one task, getting out a new set of tools, moving to another task, getting out a new set of tools, moving to another task, the so-called setup costs. Another thing that you want to think about when you think about moving from 1 worker to 2 workers to 3 workers is what we call teamwork. Teamwork is when larger groups can use a different technique of production. Think about moving furniture. You could spend all day trying to move 1 room of furniture, but if you could get a buddy to help you, you could do the job in less than a quarter of the amount of time. That's because 2 people can move furniture using different techniques than 1 person. 1 person moving furniture pretty much has to squat and push and grunt and try to move that sofa across the room. But 2 people can each pick up an end and move the sofa much, much more productively. So teamwork and specialization are always tending to increase the productivity of labor. Add more workers and you have more scope for teamwork and specialization. After a certain point, however, you notice that scope for teamwork and specialization is no longer driving the story. We eventually reach a point where additional input results in output increasing but at a decreasing rate. This is what we call the problem of congestion. Imagine you're having friends over and you're making dinner in the kitchen in your apartment. What do? You give everybody a task. You cut up the salad, you make the sandwiches, you go over and stir the soup, and so forth. Well, everybody's got something to do, but before too long, you've got so many people crowded in your kitchen that you're beginning to get in each other's way, and that reduces your productivity. As you crowd more and more television workers into a factory of a given size, eventually they're having to share tools, they're getting in each other's way, there's too much labor for the fixed amount of capital. When you've got too much of the variable input congested into the fixed inputs, then your productivity begins to fall. The workers begin to have accidents, step on each other, get in each other's way, and output begins to increase at a decreasing rate. Finally, after this point right here, after our point of maximum output, the losses from congestion are so great that additional workers actually reduce total output. There's so much congestion that it's actually reducing total output. No firm in its right mind would ever operate over in this region of its total product curve, because you can produce as much output with fewer workers. That's going to be less expensive and more profitable. So, as a quick summary, when you draw this S-shaped total product curve, you are summarizing the assumptions that economists usually make about technology. that for a firm that has fixed inputs and alters its output by changing only one input, say labor, you usually have a region of teamwork and specialization where marginal product is increasing and the curve is convex, followed by a region where marginal product is decreasing, but still positive. Output is increasing at a decreasing rate because of congestion. This is our region of diminishing marginal product. And finally, after you get past this top of the curve, marginal product becomes negative. Congestion is so strong that productivity has actually become negative. This S-shaped curve represents the technological possibilities of the firm in the short run. Next, we're going to represent marginal product in its own curve, and we'll show another curve that summarizes another measure of productivity. Series of lectures that a lot of students consider very difficult. So we're going to take our time and try to do this extra clearly. We're going to be talking about the costs of production. Now, you'll recall we've just done a series of lectures on productivity, the firm's technology. Now we're going to talk about how you take the firm's technology, what they know how to do, and combine it with the cost of hiring inputs like labor and capital, and come up with the costs of producing output. In our case, the cost of producing television sets. This information is going to be very helpful to us when we move to the next phase, finding the profit maximizing output choice for a firm. So here we are, technology, costs, and profit. We're in the middle of this stream of questions that's going to lead us to the answer, what is the best choice for a firm to make if it wants to maximize its profits? Students find this material difficult because it involves a lot of different tools used at once. We're going to be looking at charts and some simple mathematics. Then we're going to be looking at curves that represent the information in those charts. So I'm going to try to do this very carefully. I'll show you some charts, then show you the curves that go along with it. And at each stage, I'll try to remind you of the intuition behind all of it. Let me start with what I think is a very simple explanation of the relationship between costs and productivity. The first relationship we want to begin with as we start our discussion of the costs of production is the relationship between costs and productivity. In particular, costs and productivity are inversely related. That is, when productivity is increasing, the cost of production is falling. And when the productivity of your workers is falling, the cost of production is increasing. Let me see if I can make that very, very clear. Let's suppose we have a television factory. And in this television factory, we have a certain number of fixed inputs, like the size of the factory, the number of conveyor belts, the number of tools. And we also have variable input, that is, the number of workers that we hire to assemble television sets. Let's suppose we start with an assumption about productivity. Let's suppose we assume right now that one worker, given her know-how and the tools available to her, can assemble 1/4 of a television in a day. If one worker can assemble 1/4 of a television in a day, then how many workers will it take to make a whole television? The answer is, it will take 4 workers. 4 workers, each assembling 1/4 of a television, will produce for us a whole television. Now notice the point that I'm making. If one worker has an average product or an average output of 1/4 of a television, 1/4, then the reciprocal of that, 4 workers, is what it takes to produce a single television set. Notice, productivity and costs are reciprocal. If one worker can produce 1/4 of a television, then it takes 4 workers to produce 1 television. And you've got to pay those workers the wage, and that's what determines the cost of getting that television put together. 1/4 is the reciprocal of 4. If 1/4 is the productivity of the worker, then 4 is the number of workers it takes, which becomes your cost of producing the television. This idea, this simple explanation, is the basis of the relationship between costs and productivity. The more productive your workers are, the fewer workers you will need to produce your output. Now what I'm going to do is I'm going to go step by step through a description of the different notions of cost of production. We will look at the costs associated with hiring labor. We'll look at the costs associated with having a factory and tools ready for those workers to use. And finally, we'll look at the cost of producing another television set. What is the cost on average of producing a single TV, and what is the cost to produce one extra television set? The notion of average cost and marginal cost. Along the way, after I give you an example of each of these concepts, I'll be taking a break and then drawing the curve that goes with each concept, so that when you look at the picture, you won't just see a line on the page. Perhaps you'll also see a story that relates productivity to costs. That way, when we finally come to the point of using these curves to describe the firm's profit-maximizing choice, maybe you'll have some intuition that makes this more than just a technical exercise. I hope so. So we'll move now to the first concept of cost, and that is the cost of hiring the labor to produce your output, the variable cost of production. Remember, we're talking about how economists describe the productivity of a firm. Eventually, we're going to use this information when we prescribe what a firm should do to maximize its profits. But for now, we're concerned with the task of representing a firm's technology. Last time we looked at the total product curve, which tells us what a firm can do in the short run when it can vary only one of its inputs. We also described the marginal product of a firm, that is the additional output that the firm can produce by hiring an extra worker, an extra unit of the variable input. What I'd like to do now that we've discovered that marginal product is simply the slope of the total product curve, is I would like to draw a picture that puts the marginal product curve in a graph by itself. Let's look now at this diagram, and we've got another one of these now famous two-story diagrams. Remember, the trick with a two-story diagram is the graphs are related and they have the same variable measured on the horizontal axis. So in this case, we are measuring labor input on the horizontal axis in both pictures. On the upstairs picture, we're measuring total product on the vertical axis, and we're using those same numbers that we've been using all along to represent a total product, and those numbers are next door. In the graph below, we're going to now represent marginal product, and I've shown you those numbers. I calculated them before. It's the change in output that results from a change in the variable input, and these are my marginal product numbers. They're also next door as well. What I'm going to see is that when the curve is convex, that is, when the curve is increasing at an increasing rate, the marginal product will be increasing. That is, the slope is getting steeper, the marginal product is going to be increasing. When the slope is decreasing, that is, when the curve is concave, when total product is increasing at a decreasing rate, then the marginal product will be decreasing. This marginal product curve will be downward sloping. Finally, when the total product curve finally maxes out and heads south, that is, when extra workers actually decrease the total product of the operation, then the marginal product will itself be negative. So I've put the points from this diagram, from this chart. I put the points down here in the marginal product curve, and now I'm ready to connect them and draw the marginal product. So for one worker, the marginal product is 2. For the second worker, it's 10. For the third worker, it's 20, and so forth. So here is 2. Here's 10. I made a mistake there. I don't know why I had that point for 10, because I'm using this for 10 and this for 20. So there's 20. You got to be careful about this. And that means when I go back to a marginal product of, oh, I know why, because that isn't a marginal product of 10, it's a marginal product of 8. Well, I got ahead of myself, so I can mark that point off. Here's what the curve looks like. 2, 8, 20, 10, 5, 3, 1, and -1. And hey, I'll save my mistake here by making it part of the picture. I'll use that as the letter P for my marginal product curve. Hey, there's a little lesson. Sometimes you can turn your mistakes into part of the art, and that's what I've done here. Now, the marginal product curve shows me the slope of the total product curve at every point. And by connecting the dots, you can see where the curve is convex, the marginal product is increasing. Where the curve is concave, the marginal product is decreasing. And where the curve goes negative, the marginal product is below 0. So this curve represents the slope of this curve at every point. I want to throw in 2 little points of information here that you might find useful. Sometimes we write total product with an L in parentheses afterwards to indicate that total product, that is the total output that you can produce in the short run, given your technology and given your amount of fixed inputs, is a function of labor. So we write this as a function of labor. I could also write marginal product also as a function of labor. I could write MP of L, because the marginal product changes as I add additional workers to my factory. The next thing that I want to point out is that we're talking here about the number of workers who are working in the factory at a particular time. It's not like you're hiring one worker or then a second worker later in the week, or a third worker even later. We're talking about 2 workers working together for a week, or 3 workers working together for a week. See, the change in the marginal product is part of the technology. There are things that 2 workers can do to produce televisions that 1 worker can't do by herself. There are things that 3 workers could do that 2 workers can't do. Teamwork and specialization become possible as you add extra workers working together at the same time. So when we talk about the marginal product of technology, we're talking about how productivity changes as you add additional workers that are working at the same time, at once, together, over a given period of time, like a week. Finally, the last thing that I want to point out is I've been using the term convex and concave. I sometimes forget which is which, so I'll show you a little trick, a little memory trick. A memory trick, by the way, is called a mnemonic device. Some of my students were telling me the other day, I'd used the expression mnemonic device, and they started telling me that they liked these demonic devices. They thought they were helpful. So here's a little demonic device to help you. Let's suppose you're standing here on the axis looking up at a curve, and if you're looking up and you see a cave, then we say that the curve is concave. But if you look up and you're looking for a cave and what you see doesn't look like a cave, if it's bowed downwards and you're looking for a cave, well then you would be frustrated or vexed. So this is convex. So here is where you're vexed, and here is where you actually see a cave. If the curve is concave, you look up and see a cave. If it isn't, then you're vexed. The curve is convex. So now we've got a picture of the marginal product curve, which is the slope of the total product curve. And what we'll add next is another measure of productivity that you may often hear about in the newspaper, that is output per worker. And that's called the average product of labor. So we'll describing the technology of the firm. And we've been focusing on the marginal product, the change in output that results from a change in the variable input when you hold everything else constant. Now we're going to look at another measure of productivity that becomes important later in the story. I'll give you a little hint about where we're going. Remember, our main concern is being able to recommend to a firm how much output to produce if it wants to maximize its profits. Well, the marginal product turns out to answer that particular question. The average product, on the other hand, this concept that we're about to introduce, tells the firm whether it's able to make a positive profit or not. That is, when a firm is doing the best it can, is it making a profit or a loss? So let's go ahead and introduce now the concept of average product of labor. That is, the total output divided by the total labor input. When you read the newspaper or hear discussions of labor productivity on the TV news, what people are talking about is average product of labor. How much output is the typical worker at a firm producing, the average worker? We define the average product of labor, again, as total output divided by the total number of workers employed. So if we look back at the tables we've been looking at, the particular television firm we've been considering, if we have one worker producing 2 televisions, then that means on average workers are producing 2 TVs apiece. 2 workers producing 10 televisions gives us an average product of labor of 5 TVs per worker. 3 workers producing 30 has an average product of labor of 10. 440, also an average product of 10. 545 gives us 9 TVs per worker, and so forth, on down the list. These numbers represent the average product of labor for different levels of employment inside the firm. That is, for different quantities of workers hired and different numbers of televisions produced. I'll move all these numbers now next door, and we will draw a picture of the average product of labor. We will draw a graph below the total product curve that represents the average product of labor. Now, I use the red for product. I kind of like red for output for some reason. And I used the red a minute ago to draw the marginal product curve. So in order to avoid confusion, I'm going to switch to green here to represent the average product of labor. So let's do that. The average product, again, is total output divided by the total number of workers. So up here we see that a total output of 2 televisions when we have 1 worker gives us an average product of labor of 2 TVs per worker. So I'll put this in at 2 TVs per worker. And here we've got 2 workers producing 10 TVs for an average product of labor of 5 TVs per worker. Then 3 and 30 gives me an average of 10 per worker, which is exactly what I get with 4 workers producing 40 TVs. And 5 workers producing 45 takes my average down to 9 TVs per worker. And then 8, and then 7, and then 6. So if I connect the dots here, I'm going to get an average product of labor curve that looks something like this. First it's increasing, then it levels off, and then it's decreasing. And I'll label this APL for the average product of labor, the output per worker, or the amount of output that the average worker produces. Output per worker, or labor productivity. Now, before, remember we said that the marginal product of labor was the slope of this curve at any given point? There's also a geometric way to calculate the average product of labor, but it doesn't make as much intuitive sense. It's actually the slope of a line from the origin up to the curve. The rise would be output, and the run would be labor, so output divided by labor would be the average. If you're interested, you can find the average product of labor by taking the slope of a line that goes from the origin up to any point on the curve. And as the points on the curve change, the slope of the line from the origin also changes, and that changes your average. That seems a little complex, and not a lot of, intuitive assistance do we get from that, so I'm going to leave that alone and go back to the curve that I drew from the numbers that I got from my table. That's just as easy a way of doing it. I want to notice a few things about this average product of labor curve. I want to notice a few things about it. First of all, again, it's kind of U-shaped. That is, first the curve slopes upward, and then it slopes downward. We reach a point of maximum labor productivity at some point. At some point, average product of labor reaches a maximum. That is, at some point, we are getting the maximum number of televisions per worker that we can get out of this factory, given its size, given the number of tools, given our technology, and so forth. That's thing one I want to notice. The average product of labor curve is like an upside down U. At first it increases and then it decreases. It's like a hill. The next thing I want to notice is I'm going to put the marginal product curve back in this picture. I'm going to draw it again, and it looks like this, you'll recall. Okay, so here's my marginal product of labor, and I've got it in red. Notice again that the marginal product curve first slopes upward when the curve is convex, and downward when the curve is concave, and then it goes below zero when the curve, the total product curve, tips downwards. Well, notice something about the average product of labor. This is something kind of interesting, and that is when the marginal product of labor curve is above the average product curve is rising. And when the marginal product of labor curve is below the average product is falling. Now here's the intuition. If you're adding workers that are more productive than average, you're pulling up the average. Kind of like when you have a really good semester at school and you make a grade point, an overall grade point average that's higher than your cumulative GPA, you pull up your cumulative average by adding a semester that's above average. Over here, when we've got workers that are less productive than average, we're pulling the average down. Kind of like when you make a bad exam grade, an exam grade that's below your class average, you pull your class average down. You pull your own average for the course down by a below average score. When the marginal is above the average, it pulls the average up. When the marginal is below the average, it pulls the average down. That means that the marginal product curve is going to intersect the average product curve when the average product curve is at its maximum. That is, the marginal pulls it up and then pulls it down, and it intersects it, therefore, at the maximum of the average product. The intersection of the marginal product with the average product occurs at the point where the average product curve is at a maximum. Now that piece of information is going to become important later, knowing where the marginal product curve cuts into the average product curve. It cuts into it at the point where workers are producing, on average, the most televisions per worker that can be produced in this particular factory. This is the point when labor productivity is at its highest. There was a joke that we told at my school growing up about a rival school. Did you hear about the guy from our school who left to go to the rival school? He raised the IQ at both schools. Well, this is a joke about marginals and averages. That anybody who would leave our school must be someone whose IQ was below average, but he was still smarter than the average at the other school. So he raised the IQ at both places. Now, when you hear that joke and you laugh, what you're really laughing at is mathematics. You're laughing about this funny relationship between averages and marginals that makes it possible for you to take someone who's below average, move him over into another pool that has still a lower average, and raise the average in both pools. That's what this relationship between marginals and averages is all about. Well, that then completes our set of product curves. We've now done as much as we can to explain the technology of a firm in the short run. What we've done here is we've described the possibilities of a television factory that produces television sets using labor and some other fixed inputs. The firm can increase its output in the short run, but it can only do so by adding more labor. And we've described the productivity of labor by two concepts: the marginal productivity of labor, which depends on teamwork and specialization and on congestion, and the average productivity of labor, which is what we usually call labor productivity, or output per worker. We also describe the relationship between marginals and averages. When the marginal is above average, it pulls it up. When it's below average, it pulls it down. What's next? Next, we're going to take these notions of productivity and couple them with some information about input prices. And we're going to come up with a set of cost curves, a representation of the firm's cost of producing any given amount of output. We're considering how to represent your choices in the world's coolest store. You have a limited amount of money to spend on toys and snacks, and you want to spend it so as to get the most satisfaction. Last time, we looked at this equation. This is the equation for the budget constraint. It tells you how many snacks you can afford to buy given your income, the price of snacks, the price of toys, and the number of toys that you choose. When we graphed this, we got the vertical intercept, which is the purchasing power of your income measured in snacks. That is, the total number of snacks you can afford to buy, given your income and prices. And we got the horizontal intercept, which is the total number of toys you can afford to buy. The slope of the budget constraint, which is this number right here, tells you the opportunity cost of an extra toy, measured in terms of the number of snacks you have to give up. What I want to do now is show you how this constraint changes when we change some of the things in the economic environment. In particular, what happens to your opportunities when your income changes or when the price of the products changes. Let's start with your income. What happens to your feasible set? What happens to your budget constraint, or the stuff you can buy, when your income is reduced? Let's suppose instead of having $12 worth of income, you only have $6 worth of income. In that case, how many snacks could you afford to buy? That's right, 6. And how many toys could you afford to buy? 6 divided by $3 per toy is only 2 toys. Now, the relative prices of toys and snacks are still the same. We haven't changed them, only your income. The way we show a change in income in this picture is the budget constraint will shift. In this case, it shifts inward because your purchasing power has shrunk. You now have a smaller set of toys and snacks that you can afford because of a reduction in your purchasing power. If your income should increase, the feasible set shifts outwards. That is, you can afford to buy more toys and more snacks. These intercept points, again, represent your purchasing power, what you can afford to buy, how well off you are measured in terms of toys or snacks. The slope of the line, however, again, still refers to the opportunity cost of toys measured in terms of snacks. Let's look at a second possibility. Suppose now, instead of changing your income, we change the price of toys. And let's cut the price of toys in half. Now, instead of costing $3 to buy the punching monkey, you can get the same punching monkey for only $1.50. And let's suppose the same is true for the vibrating sea mine and the squeaking nun. If all of our toys are now $1.50, how many toys can you buy with a budget of $12? The answer is you can afford to buy 8 toys. 8 times $1.50 equals your $12 income. Now, your purchasing power in terms of snacks has not changed. Snacks still cost $1 each, and you only have $12 to spend. So we show a change in the price of toys by rotating the budget constraint like this until we reach its new intercept. This is the budget constraint when toys cost $1.50 apiece, snacks cost $1 apiece, and you still have $12 to spend. A movement in the budget constraint, therefore, represents a change in your opportunities, a change in what you can buy, given your income and the price of the goods. If your income changes, then the budget constraint shifts outward for an increase in income and inward for a decrease in income. But the slope remains the same. As long as prices don't change, the slope remains the same. If we change the price, on the other hand, of one of the products, say toys, then we have to pivot the budget constraint. The budget constraint moves outwards in the direction of the product that's become less expensive. Now, instead of only being able to afford 4 toys on your $12 income, you can afford 8 toys. And that's why the horizontal intercept has moved out. Notice, because toys are less expensive now, you can afford to buy more stuff than before. The budget constraint has pivoted outwards. In the future then, when you change the income, shift the budget constraint parallel. Keep the slope the same. But if you change the price of one of the goods, make sure that whichever good is becoming less expensive, that you're shifting the budget constraint outwards in that direction, in the same way that you would be shifting it inwards if one of the products became more expensive. This is how you manipulate the budget constraint to describe a change in the consumer's opportunities, a change in the feasible set of things they can afford. Series of lectures where we introduce the concepts that we use to describe the costs of production for a firm. The first concept that we're going to introduce is the concept of variable cost. The variable cost of production is the cost of hiring the variable input needed to produce a given amount of output. That is, in our case, the amount of money the firm has to spend to hire the labor that it needs to make a given quantity of television sets. In order to find the variable costs for a particular firm, you're going to need 2 pieces of information. The first piece of information we've already discussed. This is the amount of labor that the firm needs to produce a given quantity of output. And this is an idea about productivity. Remember the total product of the firm? It told us how much labor we needed to produce a given quantity of televisions. So the first piece of information you need is a piece of technological information. How much labor do we need to hire to produce a given quantity of television sets? The second piece of information that you need is a piece of economic information. That is, how much do you have to pay to get a unit of labor? In other words, what is the wage rate that you must pay your workers in order to get them to work for you, assembling television sets? Once you know how many workers you need and what you have to pay each one of them, then you've got the variable cost, or the labor cost of producing a given quantity of television sets. Let's suppose, for the sake of our example, that the wage for a television set assembly worker is $1,000 per week. That means every time a firm hires another television assembly worker, they've got to pay that laborer $1,000 per week. Let's now use that information to find the variable cost of producing certain quantities of television sets. Go back to the chart that we began with. This chart describes the production possibilities of the firm. That is, how many television sets a certain number of workers can assemble in a week. What we'll do now is take the number of workers in each case and multiply by the wage that must be paid those workers to get the total amount of money the firm has to spend on labor to produce output. For instance, if you hire one worker, you've got to pay that worker $1,000 a week for a total of $1,000. That's the variable cost of producing 2 television sets. Because after all, one worker can produce 2 television sets. That means $1,000 is the labor bill for turning out those 2 television sets. If you hire 2 workers, you can produce 10 television sets. And since each of those workers will cost you $1,000 per week, the variable cost of producing 10 television sets is $2,000. Keep going. To produce 30 television sets, you need to hire 3 workers. That's $3,000 a week. To produce 40 television sets, you have to hire 4 workers. That's $4,000 per week, and so forth. All of the numbers in this column are calculated by multiplying the number of workers you need by the wage of $1,000 to get the variable cost of producing a given quantity of television sets. Now you might ask yourself, well, what's it going to cost us to produce 35 television sets a week? Well, we can't say for sure because we don't have enough detailed information here to answer that question, but we know that it takes between 3 and 4 full-time workers per week to produce 35 television sets. So the number lies somewhere in between those two, which means the variable cost will be somewhere between $3,000 and $4,000. Again, you can imagine a fractional number of workers to give you a particular number of television sets and then multiply that by $1,000 per week to get the variable cost. Once again, the variable cost is simply total spending on the variable input needed to produce a given volume of output. What we'll do next is draw a picture of this concept.